Hello, viewers. In today's session, we are going to discuss an important topic from three-dimensional geometry, that is how to derive the equation of a straight line in three dimensions, right? So here in this class, we'll see how we can derive the vector equation of a straight line and the Cartesian equation of a straight line in three dimensions, right? So let us first consider the coordinate axis. So here we have the three mutually perpendicular axes, and this is our origin. This is x-axis, this is y-axis, and this is z-axis. Right now, suppose we have a line L, which is drawn like this. Right. So this is our line L, and let us consider a point A on this line. So here we have a point on this line L, right? And let us consider an arbitrary point P on this line. And now consider a vector M, which is parallel to this line L, right? So we have a vector M which is parallel to this line L. Now see, whenever we talk of a straight line in three-dimensional geometry, then a straight line can be characterized by two situations, right? Or we can say that a straight line can be completely defined if we have a point A on the given line, and second, we have a vector say M, which is parallel to the line L. So here we have vector M, which is parallel to the line L, right? So if we want to completely define a line in three dimension, then we must know the coordinates of a point A, or the position vector of a point A, along with a vector which is parallel to the given line L, right? So this is the first case when we completely define a straight line, right? So the first condition is we know the position vector of a point A lying on the line L, and the second one is we must know a vector which is parallel to the given line. So the second situation is the situation where we can completely know the address of a straight line in three-dimensional geometry, is that we should know the position vector of 2 points lying on the line L, right? Suppose we have a point A and point B. So we should know the position vectors or the coordinates of the 2 points lying on the line L, and in this case we do not require this vector M, right? So here when we add the second point on the line L, or we know the second point B on this line L, then we do not require this condition, that is a parallel vector or a vector which is parallel to the given line. So when we have this second case, then the diagram, it goes like this. Here we have the axis, and then we have the line L. This is our line L, and then in that case we should know the coordinates of, or the position vectors of the 2 points lying on the line L, along with the arbitrary point say P, right? And in this case we do not require this vector M, right? So the condition of requiring this vector M parallel to L is now compensated by knowing the position vector of the second point, that is the point B. So in this session, we are not going to consider this second case, right? So here we'll derive the equation of a straight line by using this condition, that is knowing the point A and knowing a vector M which is parallel to the line L, right? So here we'll not consider this case. So now here we have the point A. So the position vector of point A can be drawn like this. So this is vector OA, which can be taken as vector A, right? So this is our vector A. Now here we have the point P, which is the general point lying on the line, or we can call this point P as the arbitrary point. So the position vector of this point P is given by say OP vector is given by vector R, right? So this is our vector R, and here we have the vector AP, right? So this vector AP which is parallel to our vector M, right? So here the vector M is given to us. So now to derive the equation of a straight line in vector form, let us consider this triangle, that is triangle OAP, right? And here if we apply the triangle law of addition of vectors, then we can easily see that vector OA plus vector AP is equal to vector OP, right? So what we have done here, we are applying the triangle law of vector addition to this triangle, that is OAP, and here we have the vector OA, then we have the vector AP, and then we have the vector OP, right? So OP is the resultant vector of vector OA and vector AP. So OA is a vector A, and here we have AP, right? So here we have vector AP, and vector OP is given by vector R. So now here we have this vector AP, right? And let us express this vector AP in terms of vector M. So here we'll utilize the concept of parallel vectors. Suppose we have two vectors, right? And these two vectors are parallel to each other. Suppose this is vector A and this is vector B, right? Then this vector or this vector can be expressed in terms of each other by using the concept of scalar multiplication of vectors, right? So we can write vector A as a scalar multiple of vector B, or vector B can also be expressed as a scalar multiple of vector A when vector A is parallel to vector B, right? And here lambda and mu are some scalars. So using this concept, we can express vector AP in terms of vector M. So vector AP is parallel to vector M. So we can now write vector AP as some scalar multiple of this vector M, right? So now here lambda is some scalar, and let us substitute this value of vector AP in this equation. We have vector A plus lambda times vector M is equal to vector R, right? So this is the vector equation of a straight line in three-dimensional geometry. So here vector R is equal to vector A plus lambda times vector M. So this vector always denotes the position vector of a point lying on the line L, and lambda is some scalar, and vector M is a vector which is parallel to the given line L, and this vector R is the position vector of any arbitrary point or the general point lying on the line L. So this is the vector equation of line, and using this vector equation we can easily find out the Cartesian equation of this line L. Right now, see here we have vector A. So let us express vector A as a1 I cap plus a2 j cap plus a3 a cap. Right. So here this point A has the coordinates, that is a1, a2 and a3, right? And let us take this vector r as xi cap plus yj cap plus zk cap, where the coordinates of this arbitrary point P are given by x, y and z, right? And here we have this vector m. So vector m can be taken as say m1 I cap plus m2 j cap plus m3 n cap. So now substituting the value of vector A, vector R and vector M in this equation, we have now this equation, right? So here if we collect the I components, that is X component, J components, that is the Y component, and the K component, that is the Z component. So we can also rewrite this expression as a1 plus lambda m1, and here we have I cap, then we have a2 plus lambda m2 j cap, and then we have a3 plus lambda m3, and here we have k cap is equal to xi cap plus yj cap plus zk cap. So now comparing the I components, j components and k components on both the sides, we have x is equal to lambda. Here we have a1 plus lambda m1. Then y is equal to a2 plus lambda times m2, and then z is given by a3 plus lambda m3, right? So we can also rewrite these equations as x minus a1 over m1 is equal to lambda. Then we have y minus a2 over m2 is equal to lambda. This is m1. And then we have z minus a3 over m3 is equal to lambda from this equation. Now we can see that all these numbers are, or these expressions are equal to the same scalar lambda. So we can equate all these three expressions together. So we have x minus a1 over m1, then we have y minus a2 over m2, then we have z minus a3 over m3, right? So this is the Cartesian equation of this line L passing through this point A parallel to this vector M, and having an arbitrary point P lying on it. So this is the Cartesian equation of a straight line, and here a1, a2, a3 are the coordinates of this point A, and m1, m2, m3 are the direction ratios of this parallel vector M, right? So sometimes we can also use other notations. So we can, if we take the coordinates of this point A as say x1, y1 and z1, and the direction ratios of this vector m may be taken as a, b and c, then this equation can also be written as x minus x1 over a, y minus y1 over b, and z minus z1 over c. So now let us consider the case when this line L, it passes through the origin, right? So when this line passes through the origin O, then the coordinates of the point A may be taken as 0 comma 0 comma 0. That is, in this case the coordinates of the point may be taken as 0 comma 0 comma 0, and we can take an arbitrary point P. The coordinates are x, y, and z. Then the vector equation, that is vector r is equal to vector a plus lambda times m. This equation reduces to vector r is equal to lambda times vector m, right? Because in this case the vector a, it becomes a zero vector, because the coordinates of the point a are 0 comma 0 comma 0. That is, this point a coincides with the point that is the origin. So this is the vector equation of a line passing through the origin. And if we write the corresponding Cartesian equation, then here x1, y1, z1 are now 0. So here the Cartesian equation takes the form x minus 0 over a, y minus 0 over b, and z minus 0 over c. And we can also write it as x over a equal to y over b is equal to z over c. So this is the Cartesian equation of a straight line passing through the origin, right? So this is how we can derive the vector equation and the Cartesian equation of a straight line in 3 dimensions.